we're trying to end promptly today for the tours. Make sure we're on time for the tours. So I'm Nate. I was here last week. Pardon the mask. I have a little tickle in my throat, but you know, not COVID. I did my testing protocols. But yeah, I hope you all are doing well. Had a good week. We have a very good talk today. I forgot to put look a bio up. Look at your whole academic history. Where'd you study for? Yeah. Looked the man up himself, you know, online as well. But I think we're here to learn today about quantum mechanics, which is, you know, when I first got into physics, it was definitely one of the subjects that really puzzled me. I mean, I think there are slides in here that talk to this. You know, if you're not confused by quantum mechanics, you don't really understand it. I think that's one of the quotes. So there's a lot of interesting science that came out of quantum mechanics, and the sort of move from classical physics in the early 1900s and the sort of quantum revolution that we're going to learn about. So it's a very good talk. I'm excited to be here to listen. I've seen this talk a couple times, but it's a good one. But before we get started, Brian's not here, but I have to do his tradition of, you know, taking a few breaths, stretching up. So let's all stand up. People on Zoom, I know you see me. What's up? So that's going to be on this one. All right, so we're going to take 3 breaths. Feel your feet, you know, firmly on the ground. Try and be present, be here. Let's take 1 deep inhale. Exhale. Breath go away. Deep inhale. Exhale. Try and breathe in the things that we want, and exhale the negative. Take 1 last deep breath in. 1 deep breath out. Let's get it going. So this is Patty Fox. You're in good hands. I'll be standing by to pass around the mic. If you have questions, raise your hand. I'll try and get a mic to you quickly, or Patty will repeat the question so people on Zoom can hear it.
Okay, thank you. Good morning. As was said, my name is Patrick Fox, but everybody calls me Patty, P-A-D-D-Y. That's the best way to get my attention when you have a question. If you shout out Patrick, I'll probably think you're my mom and I'm in trouble, so I may start running away. Okay, so as I said, I'm going to be telling you a great story today about the development of quantum mechanics and telling you a little bit about what is quantum mechanics. So since it's very early in the morning on a Saturday, let's start with a joke that makes no sense until the end of the lecture. So remember there was a joke and it'll be funnier by the time we finish. All right, so here's the most important slide of every physics talk. At my stage in my career, this slide is never shown. It's sort of just assumed that everybody knows that as soon as somebody stands up in front of an audience and starts to talk about physics, the audience should ask as many questions as they have. But I'm telling you explicitly to encourage you to ask me lots and lots of questions. It'll be a lot more fun for you and infinitely more fun for me if you ask me lots of questions. So please, at any stage, just stick your hand up in the air and ask me questions. So in some sense, this is the most important slide in the talk. All right, so with the formalities out of the way, let's get started. So as was alluded to, I have a bit of a challenge ahead of me, and you have a challenge ahead of you as well. So let me tell you what this challenge is. So in your lives to date so far, you've experienced the world around you in a very particular way. You've experienced it in what physicists call a classical way. Your experiences of everyday life are described by the part of physics that we call classical physics. And so part of the problem is that our lives, our intuition for how things work is built upon our everyday experiences, and those experiences are of the classical world. So what is the classical world? The classical world is the world of people like Newton. You know, every force has an equal and opposite, you know, reaction and all that stuff. If you press on something with a certain force and it's a certain mass, you can work out the acceleration from F equals ma. And you've sort of intuited that in your everyday life, right? You don't need to solve Newton's equations to catch a ball that's thrown at you because you've developed this intuition for how the classical world works. So the classical world is the world of Newton, and if you've had the relativity lecture yet, you have? Okay, in some sense it's the world of a little bit of special relativity. As you go from Newton to special relativity and quantum mechanics, you sort of leave the classical description and go into this new modern description of the world, which is a little bit different and a little bit outside of our intuition. So you've already seen the craziness that happens in special relativity, right? Length contraction, time dilation, all that weird stuff. Well, that was a warm-up for the craziness that's about to happen in quantum mechanics. So as Nate said, nothing in your everyday life prepares you for the weirdness of quantum mechanics. It sort of flies in the face of your intuition and makes it very hard to comprehend. And that's why it took so long to discover, because it's not something you experience just by looking under a rock. Okay, so I'm going to cheat and use, I'm going to appeal to authority, which is a very cheap trick when giving a lecture, right? To convince you that I'm not trying to get my excuses in first for giving you a bad talk. I'm just saying it's going to be really hard to comprehend. So if you don't understand me, it's your fault, not my fault. That sounds like a terrible excuse. So let me tell you what some of the greats who helped develop this quantum mechanics theory thought about it at the time. So Niels Bohr, whose name will pop up again and again in this talk, said, for those of you who are not shocked when they first come across quantum theory, cannot possibly have understood it. So you're supposed to be surprised when you see this stuff. He won a Nobel Prize, not for saying this, but for some of the things we'll talk about in this talk. John Wheeler, another great of the field, said, if you're not completely confused by quantum mechanics, you did not understand it. So very similar to Niels Bohr. One wants you to be surprised, one wants you to be confused. And then Richard Feynman, who also won a Nobel Prize for his work on an extension of quantum mechanics called quantum field theory, that I'll talk about very briefly at the end, said, I think I can safely say that nobody understands quantum mechanics. Okay, so if nobody understands it, and it's my job to explain it to you, it could be a bumpy ride, but we'll have fun doing it anyway. So, so that just tells you, that's just encapsulating the statement I made that it's weird. It will turn out to be true. I'll try to convince you it's true. It's really the description of nature at very short distances. But because we don't see nature at very short distances easily, we're not prepared for the weirdness of quantum mechanics. So given that it's so strange, there's a few obvious questions that should pop into your head straight away. If it's so weird and so hard to find, how did we actually discover quantum mechanics? And I'll go through a little bit of the history. If it's super weird, what is this thing that is quantum mechanics? And why should I trust you? If it's so weird, how come you're not just making all this up? Why is it really, how are we sure it's the description of nature at short distances? So that's sort of the progression in the talk. Okay, so like I said, if you were doing physics back in the late 1800s, early 1900s, you would have probably been doing pretty much classical physics. And classical physics is the physics that was written down by people like this, people with long hair and beards, Newton, Galileo, Maxwell, and then a bunch of other people that don't fit on the slide. Once you studied all of their collected works, you would understand all of physics that we knew up to, like I said, the early 1900s or late 1800s. And one of the features, sort of the common themes of all of these great works that build up to build classical physics is that it's what's called a deterministic description of nature. That is to say that if you know all of the initial conditions, you know how everything is moving at one particular moment, and you apply, whether that be, balls on a snooker table, or tennis balls in the air, or light, or atoms, or something like that. If you know how they're all moving, you can use the equations that these people and other people wrote down to determine what will happen in the future. And it's entirely deterministic. Classical physics is entirely deterministic. So just remember that, because that's going to change. Okay. Oops. Uh-oh. What have I done? Let's try the space bar. Oh, no. Not deterministic. I can't make it advance. Ah, there we go. Probably we're going to get 3 slides at once now. Okay, so this is another way, just a graphical way of encapsulating everything I said, that if you studied, for instance, the Principia, which is this book up here, which was one of Newton's great works. And then you did enough equations and things like this, you could convince yourself that given enough information, you could work out what was going to happen in the future for any physical system you were handed. And so Principia tells you about mechanics, and Newton and others, Galileo and others worked out optics, and then somewhere on this slide is calculus and gravity and things like this. But it was sort of all of classical physics. You could study in mind. Okay. Oh, another one. Oh, these are Maxwell's equations. For those of you interested, these are a beautiful set of equations that explain how electricity and magnetism, how light propagates, all those things, and they're very concise, but hold a lot of cool information. Anyway, that's probably for another lecture. Okay, so like I said, how did we discover this quantum mechanics? Since it's not something you experience in everyday life, apparently, what is the development of our understanding of quantum mechanics? So you can sort of go back through the history of this, and you can find a moment, if you like, where you could sort of see the beginning of the end of classical physics. So all of that stuff written by those people with beards and whatnot, you could start to see that it didn't quite explain how nature worked. And to understand the beginning of the downfall of classical physics, we have to talk about something called a black body. So this is a thermodynamic system. You could think of it, if you like, as a metal box which is empty inside and has a small hole on the outside, such that, and then you shine light on the hole, such that any light that goes through the hole goes into the box, and maybe make the inside of the box a little bit of a weird shape, such that any light that falls in bounces around and can never get back out. Right? The light that enters doesn't leave again because it just gets trapped inside. So this body absorbs any radiation you shine on it. And this is a very simple thermodynamic system, right? Once you've shone light on it, this thing collects the energy and it warms up. And then it turns out that this black body, can be described by one number, which is just the temperature of the black body. You can hold a thermometer up over here and measure the temperature. This thing sort of emits in infrared radiation. And this black body is a very simple system. It should be well described by thermodynamics, which was one of the disciplines of classical physics. And so people started asking detailed questions about a black body, and they thought they knew how to calculate how black bodies worked because they'd studied all of classical physics, and classical physics includes thermodynamics. So physicists like to make plots, and one of the plots you can ask about a black body system is how much energy, if I hold the thermometer up, how much energy is coming out at a particular wavelength of light. So if I draw here a plot with the wavelength on the x-axis in nanometers, right, and the amount of energy at that wavelength, then if you've been a good student of classical physics, you could sit down and you could do a calculation based on thermodynamics, and you could calculate how much energy comes out at each particular wavelength. And then, of course, you could build something like a black body in the lab, and then you could carry out the experiment. And physics is this great collaborative, competitive collaboration between theorists and experimentalists, where a theorist will, where a theorist will do a calculation and make a prediction, and an experimentalist will do an experiment and actually take a measurement of nature, and then you'll compare the two. And what usually happens is you find that they're pretty close to one another, and the experiment and theory are in alignment, but occasionally you find something where experiment and theory aren't in alignment, and that's when things get exciting. That's how kind of physics works. Okay, so back in the day, you could calculate what a black body spectrum would look like. That's what this curve is, you know, the amount of energy at each wavelength. And here was the theorist calculation, this purple curve here. Okay, so what it said was, as I go to shorter and shorter wavelengths, or higher and higher frequencies, the amount of energy that comes out at each wavelength goes up and up and up. Okay, that was the prediction of the theorist, the classical physicist, back in the day. And then the experimentalists went out and built a black body, you know, this metal cavity, and shone light on it. And then they did a measurement of the amount of energy at each wavelength, and they found the red curve. Okay. And so this is one of those aha moments in physics where the theory, where you think you understand nature, doesn't explain what you observe in nature, and that tells you that you're missing something. And so you can see that this purple curve and this red curve are very different from one another. But you could already see as a theorist that there was something even worse, if you like, even worse than not agreeing with nature about this purple curve, because the total amount of energy that should come out of a black body, you can basically calculate the area under the curve, right? Because this is telling you the amount of energy at each wavelength. So I need to add up, you know, this wavelength, I get this much energy, at this wavelength, I get this much, and so on. And if I add up all the wavelengths, I should get the total amount of energy that comes out of the black body. So that's the same thing as saying calculate the area underneath the curve. And you can see that the measurement, the area under that curve is some number, some finite number. But if you try to calculate the area under the theorist prediction underneath the purple curve, this purple curve doesn't stop. The reason it stops here is because it goes off the plot, right? So it keeps going up and up and up and up and up as you get to smaller and smaller wavelengths. And if you calculated the area under this curve, you will get nonsense. You get an infinite number, which doesn't make any sense, right? So not only does it not agree with nature, it just is crazy on its face. And so this was the beginning of the end of classical physics. The classical prediction was that there was an infinite amount of energy in this box, which is clearly nonsense. And furthermore, it disagreed with the observations. And so this was called the UV catastrophe of classical physics, because as I go to shorter wavelengths, that's the UV end of the spectrum. And the problem is not over here. The problem is over here, right? That this curve goes shooting off at small wavelengths. So this was called the UV catastrophe. And we didn't know what to do until this man stepped up, and Max Planck, and he said, well, I don't know why, but if I make the following hypothesis, that in fact the light in this black body is not, in some sense, continuous, but is built up of discrete amounts of energy. So I can have, at each wavelength, I can have 1 piece of energy, 2 pieces of energy, 17 pieces of energy, 0 pieces of energy, but not 1.3 or 2.6 or any number in between. It has to be counted in integers. Then if I make that assumption, which was sort of out of left field at its time, then it changes. You can redo the calculation, and it moves the purple curve onto the red curve and agrees perfectly with nature. So this was, and he called these lumps of energy, he called them quanta, right? And you can see this is the beginning of quantum mechanics, so there's the word there. And so we didn't know at the time why we should do this, but if we did it, it made the theory calculation agree with nature. Oh, yes, so let me make one parenthetical statement. So this is called the black body spectrum, because it's the amount of radiation at each wavelength coming off a black body. This, as I've said, is the beginning of quantum mechanics. So quantum mechanics came out of deviations in the black body spectrum. And we also know that quantum mechanics, you probably have read somewhere that quantum mechanics describes very short distances, right? It's the physics of subatomic scales and things happening with electrons and stuff like that, so at very, very small distances. So it's an amusing statement that so far the best black body spectrum we've ever observed is this one, which is a measurement of the cosmic microwave background, which is the heat that's everywhere in the universe that's left over from the Big Bang. So we can go and we can look at a patch of the sky where there's no planets and no stars or anything in that patch of the sky. And if we go and look at it, even though it doesn't look like there's any stars or anything there, there is radiation coming towards us. That radiation is the leftover telltale signs that the Big Bang occurred a long time ago. And we can measure this radiation. We can do the same type of plot. We measure at different wavelengths. We measure the amount of radiation at each wavelength. And we get this beautiful black body spectrum. So the red is a black body spectrum for an object at 2.74 Kelvin, so just a little bit above absolute zero. And the black is the data. And whoever made this plot has multiplied the error bars. So when physicists take data, they like to say, I've measured it, and I measured it fairly precisely with a plus or minus on the error bar. They've really inflated, they've magnified for graphical reasons these error bars. So really, the measurement is incredibly precise, and it fits perfectly on this red line, which is the theory prediction. And it's the best measured black body spectrum, and it's of the entire universe, which is the biggest thing we know. So it's just it's amusing to me that the black body spectrum led us down this path to understand how very, very small physics works, but the best black body spectrum is a measurement of the biggest body we have, which is the universe. Okay, so Like I said, Max Planck made this sort of crazy hypothesis that turned out to fix classical physics. And it's so important that he got a letter named after him. He got given a letter, the letter H. So this is what's now called Planck's constant, and we denote it by the letter H. And it basically encapsulates this relationship, right? He said that light can only be emitted and absorbed in discrete units of energy, which he called quanta. And Planck's constant allows you to determine the size of these quanta. So there's this new rule of nature: light of frequency nu can only be emitted and absorbed in units of quanta. And how much energy is in a single quanta? Well, that's determined by taking Planck's constant and multiplying it by the frequency. So the energy of a single quantum of light at a particular frequency is just h times nu, Planck's constant. And this is an amazing thing. He discovered a new fundamental constant of nature, which we hadn't known up until that point. Okay, and now what is h? H, here it is. Let's look at this one. This is probably easier. It's 6.6 times 10 to the minus 34, so 0.3406 joule seconds. So it has this weird units, right, in terms of frequency, which is measured in hertz or number of cycles per second, into an energy of a quanta, and this is the number. And you can sort of start to see why it might be so hard to discover quantum mechanics. This is a very small number, right? I mean, with joules are sort of measures of energy of everyday things. Seconds is an everyday length of time. And to convert them one to the other, you multiply 10 to the minus 34. It would be hard to notice that number. Questions? None so far. Okay. All right. So since you have no questions for me, I have a question for you. So why was it so hard for us to notice quantum mechanics? We're going to do a little estimate just to see why it was so hard. You would think if somebody tells you you can only buy, loaves of bread and entire loaves, you would notice you've never been able to buy a slice of bread, right? You would sort of notice that I can only buy things in discrete amounts. So how come we didn't notice that energy only came in discrete amounts? That seems like a big deal. We should have noticed that. So let's do a quick calculation to notice to work out how well we would have to count light in order to notice that it only came in discrete amounts. So we can ask ourselves, how many quanta of light are in this room right now? If we wanted to collect them all together to check how many there are, how much counting would we have to do? So here's so let's work out how many quanta of light are around us. So first of all, we have to work out what is the energy of a single quantum. So to know that, we need to know the frequency of light. So does anybody have any idea about the wavelength or the frequency of light that we see with our eye that's bouncing around this room? Yes? It is very close to 400 to 600 nanometers. Very good. That's the wavelength. Excellent. So let's see. So I did this the other day, and I don't remember what I did. So I did 600. So that's in your range. So we need to know, so that was the wavelength you told me, and the wavelength and the frequency are related in this way, right? The speed of light is equal to the wavelength of the light times the frequency, the wavelength of the light times the frequency of the light. So I can convert a wavelength to a frequency by knowing the speed of light is about 3 times 10 to the 8 meters per second. You just told me 600 nanometers or thereabouts. So I can work out the frequency of the light in this room. It's about 10 to the 14 hertz. Okay, and here's Planck's constant, right? So I can work out the energy of a single quantum now by just multiplying h by nu. So what is it? It is about 10 to the minus 19 joules. Okay, and here's a typical old-fashioned light bulb, right? I use an old-fashioned light bulb because it's the only picture I could find on Google that showed you the power. So here is this old-fashioned light bulb is a 100-watt light bulb. What that means is it puts out 100 joules of energy every second, okay? So every second, we can work out how many quanta of light come out of this light bulb, right, by dividing 100 joules by the energy of a single quantum. And we can see that the number of quanta that come out of a typical light bulb per second is about 10 to the 20, right? And so that's why it was so hard to notice that things come in discrete amounts, because you'd have to count to a really high number to be sure, right? And essentially, when numbers get that big, measurements are continuous, because the difference between adding 1 to this and not is just a tiny change. So from any measurement perspective, it looks like you can measure any number you want, right? It's a continuously variable thing. But actually, secretly, there's always an integer number of quanta. But we'd have to account very carefully to see that in an everyday situation. And that was why in everyday life it was so hard to see quantum mechanics. All right, so that was the beginning of the end of classical physics. Now we get to the end of classical physics. Oops, is there another?
This mouse, for some reason.
Okay, oh, but there's a bunch of questions. Do we want to?
Well, I answered one. One was about empirical law.
Oh, yeah.
Gave an answer.
Thank you.
Then it was basically an incorrect model, classical model.
Yeah, an incorrect classical model, exactly. Yeah. It was a sort of a halfway house, if you like, between the two. Oh, that's okay. Oh, well, we're not missing anything down. Oh, yeah, okay. All right, so that was the beginning of the end of classical physics, was the UV catastrophe and the black body spectrum. Now, if you like, this is the end of classical physics, which is another experiment used on the photoelectric effect. So here, these are two people who did this experiment, Millikan and Hertz. And let me describe what they did, and then I'll describe how it's incorrectly interpreted in classical physics and correctly interpreted in quantum mechanics. Okay, so here is a cartoon of the experiment, right? So you have an evacuated tube, a vacuum chamber. So inside this, you've sucked out all the air, and there's nothing in there now except these pieces of metal. Okay, there's no gas in there. You have a piece of metal and another piece of metal, and some circuit in here to measure whether there's a current running around. So there's wires coming out of this vacuum tube on both sides, but there's a gap. Okay, there's a piece of metal here and another piece of metal here, but there's nothing in between. There's no air, no pieces of metal, nothing. Okay, so in principle, you shouldn't have any current running around the circuit because there's a great big break in the middle of the circuit. But you can shine light on one of the pieces of metal, right? And since this is an experiment, you get to control the frequency of the light and the intensity of the light and things like that. And you want to make measurements of how much current is flowing or not flowing around this circuit, depending on what you do with this light. Okay, so that's the setup. Then we can write down some observations of what happens when you run this experiment. So the first thing that happens is, if there's no light, there's no current. But what they noticed was if they shone some light onto this metal surface, they could arrange for current to flow around this circuit, even though there's a gap. And what they concluded from that is that sometimes when you shine light on a metal, electrons come off that metal, and they can move across the chamber, hit this piece of metal, and flow around the circuit. Okay, right? They set up a potential difference between these two plates, such that any electron that comes off this plate would be pulled towards this other plate and then would run around the circuit. So that's an interesting observation. Metals emit electrons when they're irradiated. So when you shine light on a metal, you can boil electrons out of it. Whether you boil electrons out of it depends upon the frequency of the light. So if you use light of too low a frequency, nothing happens. And then as you dial the frequency up, at some point you start to get current running around this loop. The amount of current you get depends upon the brightness, or in physics language, the intensity of the light. So it depends on how bright the light is. And you can control the potential difference, and you can work out how much energy the electrons have when they come off the plate. You can measure essentially how quickly they're going when they get boiled off, and the energy at which the electrons get emitted from the metal plate depends upon the frequency of the light. Okay, and so those are just observations you make, and then you open up your classical physics textbook and you ask yourself, what's going on here? And you remember that light is a wave, and so then you try to, we had all the Huygens principle and Newton and everything. They told us all this stuff about how light behaved, and our understanding of light at the time was that it was a wave. And we try to understand these observations in terms of the wave picture of light, and you run into some problems. And maybe the easiest way to understand this is to use an analogy. So So there are other waves out there that we know and understand maybe slightly better in our heads than light waves, and that's waves on a beach. Okay, so if you go to an island, let's say, and there's a north shore and a south shore of the island, they have different prevailing weather conditions or something, and they have two different types of waves that come in. On the north shore, there are these giant waves. They're 10 meters high, but they come in once an hour. Okay, but they're these 10-meter high waves, and they hit the beach every hour. On the south shore, there are these little 3-centimeter waves that hit the beach every second. These ripples that come in very often, but they're very small. So on the north shore, there's a high-intensity, low-frequency wave, and on the south shore, there's a high-frequency, low-intensity wave. Okay, and then I ask you, on which shore would you like to go swimming? Which shore would you feel most safe? It's clearly the south shore, right? Because the waves are very frequent, but they're very small amplitude. And on the north shore, the waves are very infrequent, but very, very large amplitude. They're 10 meters high. They're going to knock you over, spin you around, plow you into the ground. It's not going to be fun. And so it would seem if you were an electron, right? This is the analogy here, as you are the electron on the beach, or the person on the beach is the electron in the metal. You're more likely to get disturbed on the north shore than on the south shore, right? Because you know that if a 10-meter wave comes in, it's going to kick you around like nobody's business. So you would think, using that wave analogy, that it's the amplitude of the wave that's all important, and the frequency doesn't really matter. The frequency just tells you how often this thing's going to happen to you. South shore, high frequency, low amplitude, nothing happens to you. But here it's exactly the opposite, right? It was the frequency of the wave that determined whether the electron got boiled off. So this explanation of the photoelectric effect doesn't jibe with photons being waves, which is our classical understanding of how, I just said light. So how light being a wave can't be explained, can't explain these observations. So then this chap, who I'm sure you've heard of, maybe in last week's lecture or maybe before that, came along, and he made, in 1905, he wrote a series of papers. One of them was on the photoelectric effect. And he decided to take this idea of Planck's and sort of run with it. And rather than being a mathematical trick, he took it seriously. And he said that light, which we previously thought of as a wave, right? And as I told you from the beach analogy, it didn't explain the data. That light behaves as if it is a discrete bundle of energy, not just that it can only be counted that way, but it actually is a discrete bundle of energy, and that each piece of light comes in as a photon, like a single little bundle of little particle, whose energy is given by Planck's constant times its frequency. And then as soon as you do that, suddenly you can explain all of the effects of the all of the observations in that photoelectric experiment. Because what's happening, right, is these individual photons are coming in. You should think of them as particles, and they have this amount of energy. And so when a photon hits an electron, it either has enough energy to break all of the electron's bonds, right? The electron is bonded to the metal. But if you hit it hard enough, you can break those bonds and kick it out. And the amount of energy you bring into the game is determined by Planck's constant times the frequency. And that energy has to be above the binding energy. It has to be above whatever's holding the electron in the metal. If it's below that, it doesn't have enough energy to kick it out of the metal. If it has enough energy, the electron will get free and move across and complete the circuit. And so that's different. And so it doesn't matter how bright you make it, right? If you send in a bunch of low energy photons, that's a very bright, low frequency source. Each one of those photons isn't going to be able to kick an electron out. And so it doesn't matter how bright you turn it up, you'll never get the electrons moving across the tube. And so suddenly, once you decide that photons, which up until this point, for all of humankind we thought of as waves, if instead you think of them as particles, you can suddenly explain all of the observations of the photoelectric effect. So, and we could go back one by one through that list, and you'd find that making this assumption, turning a light into particles rather than waves, explains all of the observations. And so you're led to the conclusion that classical physics thinks light's a wave, but of course classical physics isn't wrong, right? It worked perfectly, with the exception of the black body and a few other things, but it worked pretty well up until that point. So what's going on? So light, Einstein said to explain the photoelectric effect, you have to think of light as a particle, and all of classical physics up to that point said light was a wave. So what is going on here? Poor old light, right? First of all, it has to decide what frequency it is, and then it doesn't know if it's a particle or a wave. And this is what's called the wave-particle duality. You've probably heard of that in quantum mechanics. That one of the things quantum mechanics did for us is tell us that light, which we previously thought of as a wave, can actually be thought of as a particle quantum mechanically. So then, sorry, I should stop. Are there questions on that? So that's the first bit of craziness of quantum, or collection of craziness. Questions? All right, I'll keep going. So then this chap showed up, de Broglie, and he asked the question that may be going through some of your heads right now. He asked the question, wait, if a wave, something we'd always thought of as being a wave, can be a particle, can something we thought of as being a particle be a wave? So does it go both ways, or is it just a one-way thing? So, so then he did something that I really like, because in a previous life I was a mathematician, and he totally abused all the rules of maths and got a fantastic physics answer. So, so I really like that. So he said, let me think about how this works one way, when something we thought of as a wave can be a particle. So I know that for light, light has no mass, but you may have heard in the relativity lecture that light can have momentum, okay? And the momentum of light is related to the energy of light. So the momentum of light is related basically as energy divided by the speed of light. But we also know from Planck that the energy for light of a single quanta is related to its frequency in this way, right? The letter H was invented for Planck, and he told us that the energy of a quantum of light is equal to Planck's constant times its frequency. So I just take this E and I replace it with this. But then we saw a few slides ago that we can relate the frequency to the wavelength of light, right? The frequency times the wavelength is equal to the speed of light. So I can do a little bit of algebra here and cancel some things, and then I can end up with just the wavelength in the denominator. So I have that the momentum of light is equal to Planck's constant divided by the wavelength of light. So he looked at this. So this is all true, nothing crazy yet, right? This is all good algebra, physics, maths, whatever you want to call it, that for light, that relates the momentum of light to the wavelength of light in this quantum mechanics description of light, when you think of light as being a particle. But he looked at this formula and he said, well, wait a second, I start with some momentum and I end with some wavelengths, right? And sure, this was for light, but I also know other things that have momentum, particles, you and me and stuff like that. They have momentum. And since this relates the momentum to a wavelength, maybe I can just skip the bits in between that would specifically for light. And maybe I can just reach the conclusion that if something has a momentum, it has an associated wavelength. Maybe that's how something that was a particle can turn into a wave. And now we call this wavelength the de Broglie wavelength. And it is true that particles, things that we think of as particles, have an associated with wavelength thanks to quantum mechanics. And that wavelength is called the de Broglie wavelength. So at this stage, you should be saying, well, I'm definitely not a wave. I know for a fact I'm a particle, or really a collection of particles, but you know, I can think of myself as a single particle if I want. This guy must be wrong. Surely I would have noticed if I was waving, or if we had wave-like properties, right? So we can calculate, why did we never notice that we had a wavelength? So what is your de Broglie wavelength? So you can, imagine however much you weigh, put it into kilograms, and then think about how fast you move around on a bicycle, walking, running, whatever, and therefore you can calculate your momentum. And then you can go back and look up Planck's constant from one of the previous slides, and you can work out using this formula what's your de Broglie wavelength, but I'll save you the hassle. Oops. Where is it? Sorry, there it is. So if you were to work out for a typical person moving at a typical speed what their de Broglie wavelength is, you get a very, very, very small number. In order to see that you're a wave, you'd have to be able to resolve distance scales that small. okay, to notice that you had a wavelength. You want to be able to see the peaks and the troughs of the wave. You got to be able to do a measurement of that distance scale. Anybody know the size of an atom or a nucleus or something in meters? Anybody want to make a guess? 10 to the negative 12. That's pretty close. Yeah, I mean, an atom is like 10 to the minus 10, and a nucleus is like 10 to the minus 15. So meters. So yeah, so this is way smaller than an atom, way smaller than a nucleus. So there's no hope of ever measuring that you have a de Broglie wavelength, and that's why we didn't see it in our everyday life. But it's true that thanks to the wonders of quantum mechanics, everything has an associated wavelength, which is the de Broglie wavelength. Oh, look, I had the answer on the slide. Okay, so that leads us then to the quintessential crazy quantum mechanics experiment. Okay, and this is called the double slit experiment for obvious reasons, because there's two slits at the beginning of the experiment. And so what this experiment does is try to uncover whether particles have wave-like properties. So let me just describe the experiment. So there's a screen with two gaps in it, okay, and then behind the first screen there's some other measuring device screen. I don't know what it is, that measures how things go through the two slits. So if you want to imagine some simple analogy of this, you have, you know, a machine that fires ball bearings, let's say, something we know is a particle. It fires ball bearings at a piece of wood, and in that wood I put two slits, and then there's a wall behind the two slits that's covered in putty or glue or something, and every time a ball bearing hits, it sticks where it hits, okay? And I run this machine for a while, it fires ball bearings at this thing. You know, a lot of them hit these pieces of wood, but occasionally one goes through a gap, and then it keeps going on its merry way and it sticks to the wall, okay? And if you ran this experiment for a while, I think you would agree, you would end up with a pattern of ball bearings stuck to the wall that looks a bit like this, right? There'd be a line behind slit 1 and a line behind slit 2 and nothing in between. Now you can do the same thing in your bath, right? You can take this double slit piece of wood and put it into a bathtub or something that you partially fill with water, and then you start tapping the surface of the water or dropping pebbles in, and every time you do that, you set up a wave on the surface of the water, and the wave ripples ripple out, and they hit the gaps in this double slit, and then of course what happens is the wave gets through these two gaps and then starts rippling again on the other side, okay? And then over here you have some way of measuring the height of the water at the edge of the bathtub, and what you know, right, is you get this crazy interference pattern because ripples come through here and they come through here, and sometimes the distance from this slit to the part of to the edge of the bathtub and this slit, these two distances differ by one wavelength, so that peaks arrive at the same time at some particular part of the wall. At some other place, a peak from one gap will arrive at the same time as the trough from the other, and sometimes it's two troughs, and so on and so forth. So you get this interference pattern. In some places the waves are tall, some places they cancel out, some places they're low, and you get this very interesting interference pattern on the bathtub wall that's indicative of wave-like behavior, right? Can you all see the analogy in your heads? Okay, you could even imagine building these experiments in your basement. So what we see is that particles, like ball bearings, lead to a pattern where there's just two lines, and waves, like on the surface of water, lead to these very interesting interference patterns where there are multiple lines, bright spots and dark spots across the surface. Okay. Now comes the fun part. You can repeat this experiment, not with ball bearings, right? Because the de Broglie wavelength of a ball bearing, as we just learned, is tiny, but with something that's even smaller and even more fundamental, an electron. But I'm pretty sure up to this point that we knew the electron was a particle, right? The electron's a particle. There's a bunch of them in every atom, canceling out the positive charge of the protons. And so electrons are particles. So we can do this experiment. Here is, it's exactly the same experiment, but just now think of these dots as different things. And when you do the experiment, you get this. So now, instead of this being a wall made of putty, it's a screen, a phosphorescent screen or something that every time an electron hits it, it glows. And you can take a picture of the screen. And what you'll see is you'll see individual glowing hits when the electrons hit, but over time, the pattern that you build up has many lines in it, which is indicative of an interference pattern. So suddenly, this electron is behaving like a wave, but you remember what happened for the wave thing. What was required for there to be an interference pattern over here? What was required was that this wave front, from dropping a pebble in or tapping the surface, that the wave front goes through both slits at the same time, right? So the wave that comes along here goes through slit A and slit B, such that on the other side, the wave can interfere and lead to these peaks and troughs. So that means that if we're getting this pattern for electrons, which is an interference pattern, which is indicative of waves, which pass through both slits at the same time, what it means is this electron has to have passed through both slits at the same time. But we think of electrons as fundamental, tiny little particles, indivisible. So again, that should be your response to this. Suddenly, when you take quantum mechanics seriously, it seems like electrons can pass through both slits at the same time. And they have to get this interference pattern. Okay, now this is all a cartoon, right? This is all you're at this stage. You're probably thinking, well, maybe I just don't believe the lecturer. He's just drawing pictures, and how on earth can I be sure that his pictures are right? So let's just go and do the experiment. I'll see if I can turn off the. So there's some audio, but I think it's all included in. So they're doing this experiment for real now, and this is actually using a real electron gun and something, you know, far more clever than the piece of wood with two slits in it. And now it takes a while to do the experiment, so we're going to speed it up. But you can see individual hits coming in one at a time, right? So these are individual electrons hitting the screen. They're sending individual electrons through the experiment one at a time. There's never two electrons in transit. And by, you know, the miracles of Hollywood technology, we can speed up the film. And it's maybe in this slide it's hard to see, but I think you can sort of see the interference patterns coming in. Right, so you can see these lines here. Oh, there we go. Now we've really sped it up. So you can all see those lines, right? I mean, you know, when you do an experiment for real, there's always dirty effects you have to worry about. It's not quite as clean as my cartoon, but you can definitely see these interference patterns, right? Where there are bright lines, another bright line, a gap in between, and so on and so forth. There's certainly not two lines like there would be for the ball bearing thing. There are multiple interference lines, meaning that the electron must have gone through both slits at the same time. And like I said, the words probably went by very quickly, but they did this experiment in such a way that there was only ever one electron in the system at a time. So this electron gun was dialed way down. So it fires an electron, and it goes through, it hits the screen, then they fire another one. So there's no weirdness of two electrons going through and bouncing off each other or anything like that. There's one electron at each stage, and then if you just add up the combination of the hits of all the electrons, you get this interference pattern. When do we need to break for a stretch? And well, can I do one more? I think I have an intermission in 1 second. Yeah. Okay. So let me. I'll break in 1 second. You can come and ask me questions. I'll stay down the front and stuff. But I just wanted to make one quick point about. So what I've been describing up until quantum mechanics was built a lot on these things, Gedanken experiments. So that's the German for thought, I think. So one of the amazing things about the development of quantum mechanics is it was somehow developed sort of ahead of the technology, right? So we didn't do the experiment I showed you the video of until decades later. I think that's from the 1980s. And part of the reason was, as you saw, right, to see a de Broglie wavelength of U, you'd have to measure a very, very, very short distance. To see the de Broglie wavelength of an electron is equally, well, not quite as hard, but still hard. So to do that experiment with electrons for real, it's not like taking a piece of wood, like I was saying, and sawing two gaps into it. You have to engineer things down at the atomic scale. So the type of double slit you have to build, the two gaps you have to use are essentially the same as the distance between atoms in a metal. So it requires a lot of technology to do this. I think I've said it there. So the atomic spacing in metals. So we had to develop quantum mechanics by thinking about how the world would work if we could do the measurement. And then in many cases, only years later were we capable of actually doing the measurement and confirming that quantum mechanics was correct. And so, that's just part of the history. So that double slit experiment was a thought experiment originally, a Gedanken experiment that led people to understand how quantum mechanics works. And we'll talk some more about it in the second half, but I'll stop now. I'll stay down here. You can come ask me questions. And if you don't want to ask me questions, you can go take a quick walk.
So before we break, I guess we'll see what we can do questions. So everyone, there questions? Really? Oh, here we go. All right.
Thank you. I just was wondering, how can a particle such as an electron be in two places at once if it's only one electron being shot forward in this experiment at one time?
Yeah, that's the weird thing. We'll talk more about it in the second half, but that you're asking exactly the right question. How on earth can an electron, which is we think of as an indivisible particle, go through both slits at the same time? So in some sense, you're asking the question, what's waving? Right, where is the wave in this game? And we'll talk about that more in the second half, but that's the right question.
Also, determined that you needed two slits to measure this experiment.
So what we wanted to do, right, is to try to find an experiment where a particle and a wave behave very differently, and so that we could try to tell them apart. And if you remember, the big difference here is that a classical particle, can only go through one slit at a time. So you could build many slits here, but it would only ever go through one. So on each individual instance, it would only know about one slit. Whereas a wave, which spreads out into a wave front, can go through multiple at the same time. So you could repeat this experiment with 3 or 4 or 5 if you wanted, but 2 is the first number where you get to notice a difference between how a particle and a wave behaves. So we do 2 because it's the simplest.
One more, and then we'll...
Yeah. And I'll stay up here so you can come down and ask me questions. Good. That's sort of related to the other question. What's waving? So this happens even if the electron's moving through vacuum, so through nothing. So I don't know if they talked about Michelson-Morley experiments in the special relativity. So for a while, we did think that light and other things had to be moving through. So here, when I said wave, I was thinking wave on the surface of the water, and there it's very clear, right? The wave is on the surface of the water. You need the water. So when we thought of light waves, we thought there had to be something else wobbling around, just like there is for water. And we invented this thing of the ether, right? And that was wrong. And the same is true here. For this wave that we're talking about for quantum mechanics, there doesn't have to be anything around. There doesn't have to be an ether or anything like that. It's a wave just in space and time. Yep, and we'll get to more of it in the second half. Don't worry. All right, the second half. Thanks for all those great questions. Don't be shy in asking them during the talk. All right, so I think some of you in the audience alluded to this, and then some of you who came down to the front sort of asked related questions, which is what is waving? So now we talk about the mechanics, the technical side of quantum mechanics. We'll do a tiny little bit of math, so I will solve your first quantum mechanics homework problem for you. So take careful notes, and then we'll talk about some of the predictions of quantum mechanics. So what is this thing that's waving? So quantum mechanics at its core is built around something called the wave function, right? So there you see the word wave is in its description, and it's so important to the description of quantum mechanics that pressed the wrong button. Okay. That I drew so it's typically denoted by this Greek letter psi, and I try to put it in a very, very big font because it's very, very important. And what this thing is at the very core of quantum mechanics, right? This thing is used to describe all of the stuff I've talked about so far. If you open up a quantum mechanics textbook, this is the thing you'll see. And this is the thing that's doing all of the action in quantum mechanics. And this thing basically is a function, which means it's a machine, right? You give it some inputs, in this case, a position and a time, and it gives you an output. And it's that thing that we can investigate and ask questions of. And what is the output? Well, the output, actually, you have to square it, but that's a technical detail. But the output of this wave function is a probability. So that's what the information we get out of quantum mechanics is a probability for something to happen. So remember I mentioned very, very briefly at the beginning that all of classical physics was deterministic in nature, right? It determined exactly what was going to happen. Well, quantum mechanics is still deterministic. I will show you on the next slide a wonderful equation that tells you how to calculate how the wave function behaves. You give me the wave function at some particular time, it will determine the wave function at a future time, and all you have to do is solve an equation. It's entirely deterministic, just like it is for Newton's equations or any of those classical equations. The only difference is that in quantum mechanics, the thing you determine is the wave function, and the wave function only tells you a probability for something to happen. So it doesn't tell you with certainty what will happen, it tells you with certainty what is likely to happen. Do you see what I mean? And so that's the difference. So the evolution of the wave function is deterministic, but all the predictions that come out of it are statistical in nature. So it's a probabilistic theory. Okay. So this chap, Schrodinger, wrote down this equation. It looks kind of crazy, right? But this is, physicists love this equation. This is the Schrodinger equation. This is the description of things like electrons moving around. And it's an equation for this wave function now written in an ever so slightly smaller font. And you see that it has h's in it, right? That's Planck's constant. So you know it has a wave function, so it's going to be a wave description of nature. It has Planck's constant in it, so it's going to be quantum mechanical because we need Planck's constant for quantum mechanics. And it describes how this wave function behaves. So there's some bunch of symbols, and this V here basically encodes, is a mathematical way of encoding the situation you're asking a question about. So if it was the double slit experiment, we would write down a V for the double slit experiment. Okay? And once you have an equation, all you have to do is solve it, right? It's not that hard. Maybe you need a computer, maybe you need a very, very big piece of paper, but in principle, once you have an equation and an initial condition, you can solve it and determine what will happen. And that's exactly what you can do with this. But as I said, the only thing you can determine is the probability of something to happen. Okay, so let's take this. I don't know how many of you study physics at school, but at some point you probably were bored to tears doing those balls rolling down an inclined plane. You know those types of problems? The ones that turn everybody off science. So this is the quantum mechanics equivalent, if you like, of a ball sliding down an inclined plane. But the reason I'm going to show it to you in detail is because it's very important when you apply it to nature, as we'll see on the next slide. Okay, so this is what's called particle trapped in a box. So you can imagine that there's a box on this table, and I have a ball inside it, and the ball is bouncing backwards and forwards inside the box, but the box is closed, and I haven't told you anything about it. And let's imagine secretly that that ball is an electron, and we know that everything's quantum mechanical, so this is a quantum mechanical ball bouncing backwards and forwards. So, so now all I have to do is solve this equation for this quantum mechanical ball bouncing around inside a box, and I can work out the wave function, okay? Now, it's a box with hard walls, so I know that the ball cannot be outside of the box, right? There's no way for the ball to get outside of the box. So I know what the wave function looks like, or at least I have the beginnings of an understanding for what the wave function looks like. The wave function has got to be 0 outside of the box, right? So this boundary here is the left-hand side of the box, this boundary here is the right-hand side of the box. The wave function is 0 outside. And now it turns out that this equation although it looks really ugly, it sits in a class of equations, of what we call wave equations, and exactly the same equation, but with different numbers, but basically the same type of equation, shows up when you try to work out how a guitar string works. Okay? And you have good intuition for how a guitar string works. So imagine you have a guitar string and you have it held down at both ends, and you want to create a standing wave, a nice note on the guitar string, right? There's certain places you can pluck the guitar string to make a good note. One of the places you can pluck it is in the middle, right? So that there's half a wavelength in there, right? And then nothing outside because the string is held down. And that turns out to be true for the quantum mechanics case as well. So you can have a wave function that looks like this. You can have a guitar string that looks like this, or one that looks like this, right? You always have to get the right number of nodes or the right number of wavelengths put in so you have a standing wave on the guitar string and it sounds nice, right? And you know that as you go up and up and up, you get higher and higher frequencies, okay? And those are just all the different notes you can make on a string on a guitar. And so that's your first quantum mechanics homework problem, to determine the wave functions for a particle trapped in a box. And these are the wave functions, just like the guitar strings. And then I told you that the rules of the game were, if you figured this thing out, to work out what's going to happen, you have to work out this thing. So just square it, right? So we go back here, and I just square the wave function. And this now is telling me, what is this wave function telling me? It's telling me the probability of finding the particle somewhere in the box. So this is the left-hand edge of the box here. This is the right-hand edge of the box at L, so between 0 and L. And this is the probability of finding it in each place. Okay? So now I have this particle in a box, and I let you open the box and look inside. Okay, you look inside, and you see that the particle is, let's say, 1/3 of the way over from, it's at 1/3, or L over 3, whatever it is, right? So actually, that was a bad choice. Let's do L over 2. So it's right in the middle of the box. And I ask you, well, what's the wave function of this particle? Right? Because that's the only thing I want to know. I'm a quantum mechanical physicist. What's the wave function of this particle? Well, with one experiment, you can't tell, because you know that the particle was in the very middle of the box. So you know it can't be in this wave function, because the probability to be in the middle goes to 0 in this one. And it can't be in this one either, because it's also 0 in the middle. And then there's another one with a 6 on it, and so on and so forth, right? Which it can't be. But you can't tell if it was this one, or this one, or 5 or 7, blah, blah, blah. Okay? So from one measurement, you can't tell what the wave function of the particle is. You can't tell what which one of these wave functions is related to the energy of the particle as well. So you can't tell. But if I give you hundreds and hundreds of boxes, and I say they're all the same, I put the same particle in the same box just 100 times. So then you get to open the box 100 times and do 100 measurements. And slowly over time, you'll find one that's in the middle, and one that's over at the edge, and over edge somewhere else. And maybe over enough time, just like those electrons hitting the screen, you accumulate enough information to work out what the wave function is. But you can't tell from one measurement alone, right? Because all you're getting is a probability for it to be somewhere. And all of these, many of these wave functions have some probability for the particle to be in the middle. Okay, and that's the big difference between the way quantum mechanics works and classical mechanics works. All right, questions? Yes. Oh, L is just, so the question was, what is L? And L is just the size of the box. I should have said that. So I'm imagining, you know, we don't want to talk in terms of numbers. We just call it some letter. The box is L meters long. Okay.
There's one question from Zoom.
Yep.
So why does the particle have a higher frequency the higher it is in the box?
Sorry. Yeah, this is a bad, I should have explained more. These are not higher in the box. You should think of these as all being the same box. But the reason I've drawn these wave functions higher is, as you said, they have a higher frequency. And as we saw, or a shorter wavelength, and as we saw earlier from de Broglie, right, the wavelength is inversely proportional to the momentum. So these ones with a shorter wavelength have a higher momentum, and therefore they're moving faster, they have more energy, and so on. So I've just drawn these stacked like this because these are arranged by energy. This is the lowest energy state. This is the next energetic state. Then this is another energetic state, so on and so forth. And actually, this one is, let's see, this one is 4 times as energetic as the ground state. This one is 9 times as energetic, 16 times. So the height is meaning the energy. But they're all sitting, all the particles are sitting on the table. They all have the same, it's the, and that will be very important for the next slide. Yes, thank you for asking.
I was wondering how you would measure the position of the particle.
So think of this as like an Amazon shipping box, right? It has walls, and it's sitting on the very bottom, just bouncing backwards and forwards, and I've closed the lid. And then I'm going to open the lid and let you look inside, but the ball can't escape because it's just bouncing backwards and forwards in the bottom of the box. And then you open it and you take a photograph, and you say, oh, it was in the middle, or oh, it was over by the wall, or it was somewhere in between. And then I give you hundreds and hundreds of these. I've spent a lot of time arranging for these to be identical. And you get to open the box, take a photograph, open the box, take a photograph. Does that make sense? Okay. Oh, this is great.
What is the infinite well probability?
Oh, that's a fancy maths way of saying a particle in a box.
What does it mean?
It means that this is oh goodness, yes. It means that this is an infinitely deep potential well, so the particle can't escape. So you can think of this in energy space. And suppose I throw you down a great big hole in the ground, right? Such that you could never climb out. The only way you could move is around the bottom of the well, right? And that's just math speak for a particle trapped in a box.
Have an infinite level, like number of energy levels, then how would you ever be able to determine which wave function it is? Good. So it's true there's an infinite number of possibilities in this situation, right? But suppose I did arrange for them all to be in the same state, and you opened them, and slowly over time you saw, you measure where it is in each one, and you put those dots on this plot, just like we did with the electron. And suppose the dots all started to line up on this thing here, like that. Then you would know that that was the wave function. See what I mean? It's true you have an infinite number of possibilities, but I'm not going to spend the energy to make one way, way, way up in the tower. But with enough measurements, you will be able to map it out, right? Does that make sense? And it may be this one. I mean, I'm not, but oops, what have I done? All right, lecture's over. Okay, oh man. Try and do it this way. Where were we? Right, so why am I telling you how to solve a homework problem? That seems kind of boring, no? Well, the reason I'm telling you this is because this situation is, as well as being a homework problem, is very close to the situation we find inside an atom. So electrons in an atom, in the Bohr model of the atom, right? Here we are, the nucleus made up of protons and neutrons. And then this is not the scale, but we think of these electrons orbiting around the nucleus. And they whiz around, these are charged, negatively charged electrons whizzing around the nucleus, right? And if you had this model of the atom, which is a reasonably good model of the atom, and you were a classical physicist, you would remember that when something goes around on a circle, right, it can have a constant speed, but it's constantly accelerating, right? Because its direction is always changing, so its velocity is always changing, so it's accelerating. So you have a charged particle accelerating, because it's going around in a circle. And then you would go and you'd open up Maxwell's equations and you'd remember how those work. And you'd say, oh, I remember that when you accelerate a charged particle, it radiates light. Okay, so these electrons, which are constantly accelerating, are constantly emitting light in the classical picture. And when you emit light, you lose energy, right? So they have to slow down. So then they need to be orbiting slower. And so then they should change the radius of their orbit and so on and so forth. And you would do this calculation, and you would find that this model of the atom, which actually explains the atom pretty well, is unstable, right? These electrons would instantly fall into the nucleus and be done. Chemistry would be over. We wouldn't be here. So a classical model of the atom like this is an unstable model of the atom. However, quantum mechanics comes to the rescue because these electrons described by quantum mechanics, and they need to have a wave function. And it turns out that the wave function for the electron is very similar to the wave functions I drew here, as long as you take the two sides and join them up. Okay? So you sort of have to take this thing and bend it around on a circle. And it turns out that just like here, the only wave functions that were allowed were the ones that fit into the box, right, with a discrete number of wiggles, right, 1, 2, 3, 4, so on and so forth. The same is true for the electron inside the atom. You need the wave function to be such that it fits into its orbit, just so. So the wave function has to have the right number of wiggles such that it joins back up to itself when it comes around the circle. And that wave function is allowed, and this wave function is not allowed, because by the time it comes back around, it's not in the right place to join back up with itself. And that's only because of quantum mechanics, that these wave functions have to have this very particular structure, right? Because they're waves, they have to fit into the space just right, because the electrons are described by waves. And this all boils down to the fact that angular momentum is quantized, just like energy is quantized, because it's a quantum mechanical system. And so that means that once you have the least number of wiggles you can fit on the circle, right, there's no other wave function it can change into. So unlike the classical system, where you constantly accelerating, so you could always emit some radiation and fall in, you can't do that in the quantum mechanical atom. Because once you've fallen down to the smallest number of wiggles that obey all the rules of quantum mechanics and fit into the orbit, you can't go any lower than that. Okay, just there's no wave function you can find that allows you to have a smaller orbit. And so there is a ground state, there's a lowest possible state, there's nothing below it, and the atom suddenly becomes stable. So the reason atoms are stable and we can have interesting things like you and me is because of quantum mechanics. So thank goodness for that. There was a question somewhere. I don't remember who had the hand up. Did you have your hand up? Or you changed your mind? Okay, good. So not only does quantum mechanics allow there to be interesting chemistry, it allows us to understand that interesting chemistry. Like I said, the exact positions of these orbits, right, are determined by the rules of quantum mechanics, that things are quantized, the wiggles have to fit in just so. And so that means that for every atom, there's a unique set of energy levels for the electrons that's determined by the type of nucleus there is, and so then the energies of those energy levels are determined, just like the homework problem. And so that means that if you do things to these atoms to bounce the electrons between energy levels, so if you heat up an atom and the electrons get heated up and get moved up to higher energy levels, when eventually this thing cools, the electrons will jump down to the vacant energy levels that they came from. And when they do so, they'll emit some light, but they emit light at a very particular frequency, right? Because these energy levels, there's only certain energy levels that solve the wave function equation, and the distances between those energy levels are therefore very, very determined. And so the energy difference between these levels are determined. And we know that once you have an energy, you can determine through Planck's constant a frequency. And so when these electrons de-excite, they emit at a very, very precise frequency. And it turns out that every atom has its own set of frequencies or own set of energy levels associated with it, which is like a fingerprint for the atoms. And this allows us to identify atoms by their emission or absorption lines. So this is what happens if you take a test tube of some gas and you heat it up and then look at what comes out. You would get light at very particular frequencies, right? So this is like a continuous spectrum, and this is a sun or something. And this is what happens if you have just a single element. You get a particular line, and this is the converse. If you take a light bulb and shine it through a test tube of gas and look on the other side, you would find that certain places in the spectrum are missing because it absorbed just those frequencies. So you can use this to identify elements. And this is all at its very core because of quantum mechanics. So a parenthetical amusing observation is that
that actually predating quantum mechanics, we knew this was true sort of phenomenologically. We'd figured out that every material had a particular sequence of lines, and we'd even worked out a formula that fits it. And that formula, once you know quantum mechanics, you can derive, and so you can see where it comes from. And we went out and we looked everywhere we could for these lines. And one place we looked was on like the surface of the sun, right? We looked for the light passing through the surface of the sun, and we saw a collection of lines, and we compared those lines to our big book of lines for all the materials we knew about on the Earth, and we found some lines that didn't have any corresponding entry in this big book of all the fingerprints of the elements, and that's how we discovered helium. So helium is the second most common element in the universe, but it's very uncommon on Earth and very hard to find. But it's copious in the sun, and we found it in the sun. So it's an extraterrestrial element. It was found first outside of the Earth. Yes.
Zoom question. So if you go back to a couple slides, we're talking about angular momentum. The question's about angular momentum. What do you mean by the lowest orbital has L equals 1, nowhere to decay to?
Yeah. So
and also, what is angular momentum and how is it calculated, which might be more harder to answer.
So angular momentum, in some sense, is so if you spin around in circles, you know, it's the ice skater thing. It's to do with the size of the orbit and the speed at which you go around it. So it's the product of momentum and radius, but it's how much spinning you have, how much rotational energy you have to determine your angular momentum. And this is just a mathy, physicsy way of saying the thing I was saying before about fitting the wave function in. So the lowest orbital has angular momentum 1, and it's there has to be angular momentum because it's going around in a circle, and there's no integer smaller than 1, right? So you can have angular momentum 7, and that would be one of these excited states. But once you've lost some energy, you've got to come down to another integer, and you're going around in a circle, so that integer has to be non-zero. So 1 is the smallest non-zero integer, and that's the reason why you can't decay anymore. In a classical world, this number doesn't have to be an integer. Right? In the same way when we counted energy, we had to count it in quanta. Turns out angular momentum is also quantized, and you have to count it in integers. And that fact that 1 is the smallest integer is what keeps the atom stable. I hope that answered the question. Okay, good. So the last piece of craziness before we finish up is the Heisenberg uncertainty principle. So some people in the break were asking me about this, so I hope this addresses their questions. So Heisenberg's uncertainty relation, here's Heisenberg himself, won a Nobel Prize for this observation, states that the more precisely the position is determined, the less precisely the momentum is known, and vice versa. So a maths way of saying it is the uncertainty in position times the uncertainty in momentum has to be bigger than a number, and that number's got an h in it because this is a quantum mechanical thing. So it's h bar over 2. And the reason Heisenberg is true, Heisenberg's uncertainty relation is true, is because quantum mechanics is a wave description of nature. It is to do with wavelengths and whatnot. So what are the repercussions of the Heisenberg uncertainty relation? This is another fact about nature, but what does it imply? Okay, so let's go back to, let's talk about what it means. I think somebody was asking me this question in the break. So what it turns out to mean is that when you do a measurement on something like an electron, you actually change the electron in the process of doing the measurement. You alter the behavior. So how, at its very core, do you measure the position of an electron? Or how do you measure the position of anything, for that matter? What you do is you shine some light on it, and you see where it is. Okay? So in this case, we'd have to use not only light, but a microscope, because an electron is small. And to see precisely where an electron is, turns out you want to use light of a pretty small wavelength, because the uncertainty in where an object is determined by the wavelength of the light. Right? The bigger the distance between the peaks and the troughs,
the less sure you can be about where exactly in that peak trough distance the object is. So if you want to measure something very precisely, you want to use very short wavelength light. Excuse me. So you want to use shorter wavelength light, right? But de Broglie told us how wavelength of light is related to the momentum of light, right? And he said that if you use a short wavelength of light, that corresponds to a high momentum. Now you know that if you want to measure if you take 2 snooker balls on the table and you throw the cue ball at the object ball really fast, and the object ball is going to move off very quickly. If you throw the cue ball very slowly, the object ball will move off very slowly just because of conservation of momentum. And so now if we follow Einstein and we think of the wave of light as really being a particle of light just for a moment because of this wave-particle duality, and now we're firing short wavelength light or high momentum light at the electron, we know that when the light hits the electron, it's going to kick the electron and move it off in some direction. The light is going to come up here to our eye and we're going to see it, and we're going to say, ah, the electron was here. But in the process of measuring it, we've given it some momentum, right? And the better we want to know the position, the shorter the wavelength, and therefore the more the momentum of the light, and therefore the greater the momentum of the electron afterwards. So the better we try to measure the position, the more we mess up its momentum, and vice versa. And the amount by which these occur are determined by the Heisenberg uncertainty relation. So now we can go back to the double slit experiment and see if we can try to outwit nature, right? And see how nature basically outwits us. So you could have asked me this question, nobody did, but you could have asked me this question. Well, you're saying an electron's going through both slits at the same time. That sounds like total nonsense. So I'm just going to build a better experiment than you, and I'm going to put a microscope on one of these slits. And I'm just going to watch very, very carefully every time you send an electron through, and I'm going to see if it goes through this slit. And if I see it going through this slit, I know it didn't go through that slit, and therefore I'm going to have outwitted you. And this nonsense about an electron going through 2 slits at the same time, I'll just disprove you. So how would you go about doing that? Well, you would have to put like I said, a microscope on one of these slits, and you'd have to shine some light in. And what frequency of light would you have to use? Well, you'd have to use a wavelength of light that's smaller than the distance between the slits, right? Because if the wavelength of the light you're using is bigger than that distance, then you can't actually tell which slit it went through. So you have to use a very short wavelength light, smaller than A. But as I just told you, if you're measuring the electron using light by shining it into that gap there, and you're using very short wavelength, very high frequency light, you're also using high momentum light. And so when you do measure the electron going through that slit, you will perturb its direction, right? You'll perturb the momentum. And the amount by which you'll perturb it will be determined by the Heisenberg uncertainty principle. So you do all the maths, you follow through all the rules of quantum mechanics, and what you find is if indeed you measure the electron in that gap, you give it a certain amount of momentum at the time you measure it, and the amount of momentum you give it is just enough to move it from one of these fringes to the other fringe. And so in the process of measuring that the electron went through that gap, you just messed up the interference pattern, right? And you don't get the interference pattern back, you just get lines. So if you try to outwit my experiment by putting a microscope on it and measuring that the electron goes through slit 1, then indeed you don't get the interference pattern because you know the electron went through that slit. And the reason you don't get the interference pattern is because of the uncertainty relation and this. Yes? Oh, I can repeat the question. So the distance between the slit and the screen basically just determines the distance between the fringes. And so you want to push these far enough back such that the distance between the fringes is measurable. But this effect that I'm talking about won't change. Once you measure the once you try to measure which slit it goes through, the perturbation on the momentum you give it is enough to mess up the interference pattern. So Heisenberg basically says, as soon as you do make the measurement such that there's no way the electron could have gone through both gaps, then there's no interference pattern to happen, and you don't get an interference pattern. If you don't do the measurement, then you don't know which slit the electron went through, and in principle it could have gone through both, and therefore it can interfere with itself and lead to an interference pattern. But as soon as you know which one it goes through, then they can't interfere. Right? So it's really this wave of probability that you don't know where it's going, and this wave, just like in the bathtub, where the wave of probability can go through both gaps and therefore interfere with itself and give you an interference pattern. So it's a probability wave. All right. Oh, and I think this answers your question, but too complicated to go through. Okay, let's see. So we have like 10 more minutes. Good. Okay. So this fact that I don't measure which slit the electron goes through leads to the interference pattern is because I don't know for a fact which one it goes through, and so there's a chance that it went through one or the other, and so therefore the wave of probability can go through both, and so it can interfere, right? And this gets back to somebody's question asking about what's going on when you're not looking. So when I'm not looking at the slits, the electron could go through either of them, and therefore I get the interference pattern. As soon as I look and I know, I don't get the interference pattern. As soon as I take a measurement and learn, I destroy the interference pattern. So up until the moment I make a measurement, the wave function, which is what describes all of quantum mechanics, basically has to contain a description of all the actual possibilities that could happen, right? And so the wave function is this big function that's basically a list of all the possibilities. And then when you make a measurement, the jargon is you collapse the wave function. So when you make a measurement, it picks one of all the possibilities it could have been, and then the wave function is put into that state. So I don't make a measurement on the slits. The wave function says it went through the left-hand slit or it went through the right-hand slit. There's a 50-50 chance it could be either. That's what the wave function describes, and then that leads to the interference pattern. I make a measurement, and I say it goes to the left one, and so therefore the wave function is collapsed, and now it's just described by only going through the left-hand slit, and therefore there can't be any interference pattern. So, and this is related to the 100 of experiments I had to do for the particle in the box, right? In principle, it could be in any one of those energetic states, and then I open the box and I do a measurement, and it collapses into the one you observe it to be. So the only thing you can do with quantum mechanics, as I've already stressed, is you get a probabilistic outcome. You basically have to learn how these list of all these possibilities are weighted in the wave function, and to do that, you have to do the experiment many, many times, right? Because you can get any answer on the first experiment. You could have just got really lucky and got the very, very unlikely thing on the first experiment, and then when you do it 100 more times, you find you get the other possibility. And so then you learn that the distribution of the wave function is such that there's a very rare case that happens 1 in every 101 times, and there's the other case that happens 100 out of 101 times. So do you see what I'm saying here? This wave function is kind of a weird thing. It collects all the possibilities at one time, and then you have to keep probing it again and again by doing experiments. So that leads us to another crazy thing about quantum mechanics. So I don't know if it was really Schrödinger that thought of this, but so one of the early developers of quantum mechanics, you know, actually it wasn't Schrödinger, was it? It might have been Einstein. Anyway, they constructed the following Gedanken experiment. Remember, I talked about thought experiments as opposed to real experiments. This is very much a Gedanken experiment. They said, this sounds crazy to me. How can you possibly have a description of nature where it contains a list of possibilities at the same time? Surely it's got to be a description of one or the other. It can't be a description of the 2 possibilities or the 20 possibilities all at once. That sounds very strange. For instance, what if I had a box that was you couldn't see into from the outside, and it contained the following 3 things. It contained a piece of some radioactive element, I don't know, uranium or something, and a detector that detects radiation,
And this there's enough of this radioactive element that there's a 50-50 chance one of the atoms will decay in the next hour, right? And there's a detector that decays, like a Geiger counter or something, that detects whether an atom is decayed. And if it's decayed, it drops a hammer on a vial of cyanide gas, floods the gas with cyanide, floods the box with cyanide, and kills whatever inside. Oh, and I forgot to say there's a cat inside. So I'm going to put a cat, radioactive element, and a vial of cyanide all in the box. And so I know there's a 50-50 chance that when I open the box, there'll be a live cat in there, or really an angry live cat. And when there's a 50-50 chance that when I open the box, there'll be a dead cat. Okay, so I know that everything is quantum mechanical at its core. So what is the quantum mechanical description of this box? Well, or in particular, the cat in the box, the only thing we care about. So the quantum mechanical description of the cat in the box is the superposition of the two possibilities, right? It's a live cat and a dead cat. And there's a 50-50 chance, so this alpha and beta here are like, 50, such that it's 50-50 probability of getting both, or getting either rather. And so that is the quantum mechanical description of the wave function of the cat in the box. But this is clearly nonsense, right? Because a cat can't be both alive and dead. A cat knows whether it's alive or dead. So what's going on? And this is one of the weird things about quantum mechanics, is that it leads you into these sort of strange philosophical debates, right? That this all sounds very good for an electron. If I built up a similar type of Rube Goldberg machine for an electron, then I could imagine that the electron is in a superposition because electrons don't have feelings, cats do. So what on earth is going on? So this leads, and really at its core is this problem about collapsing the wave function by opening the box. What does it mean to collapse a wave function? Who am I to say that opening the box is the thing that collapses the wave function? Maybe the cat thinking about why it's inside a box collapses the wave function. But at the experimental level, when we're doing this with electrons, we know what it means to collapse the wave function because we know that we are going to take a measurement at some point. But then when you do it with bigger objects like this, it gets very confusing. So this leads you down the path of trying to understand all the possible interpretations of quantum mechanics. So what is it that collapses the wave function? When I did this, somehow I was thinking of me as an experimenter doing this with cats as being a classical object. I didn't really have a quantum mechanical description of me. And this leads you into a whole slew of possible interpretations of quantum mechanics. There's something called the many worlds interpretation proposed by Everett back in the 60s. There's models where you slightly tweak the Schrodinger equation such that there's an extra term that leads to the collapse of the wave function at a random way. There's Bohmian hidden variable descriptions of quantum mechanics that don't quite work. And the thing is, when any one of these that actually works, all predicts the same outcome in physics experiments. So there's a famous quote attributed to David Mermin that is the sort of mantra of the working physicist, which is shut up and calculate. So leave this to the philosophers. Let's just ask me a question about something I can measure. I'll give you a definitive answer, and it will be right if I do my calculation right. Because quantum mechanics works. Okay, I think I have maybe 2 more minutes. So, yep, okay. So let me tell you what's changed in, a lot of the people whose faces I showed you were either died in the 1600s or did their physics work in like the 1910s or the 1920s. So it might feel like quantum mechanics is done and dusted. It's all over, people figured it out a long time ago. But I'd actually say that we're entering into a really interesting time for quantum mechanics because it's gone from being, we've now studied it for long enough. We've worked out how quantum mechanics works. So we can now use quantum mechanics as a tool to do other types of physics, right? So in the past, quantum mechanics was a way we learned about how things worked at short distances. We learned something about nature. But now we can manipulate quantum mechanical systems very, very well. We understand quantum mechanics so well that in some sense it's become a little bit intuitive. The classical physics is what used to be intuitive, and now we study quantum mechanics enough that we can get some intuition for it. And we can now use it for all sorts of wonderful things. So you've probably heard about quantum computers that allow us, through the power of superposition, the fact that you can put a state into a superposition of many possibilities all at once, allows you to build new types of moving parts inside computers. So in an old-fashioned computer, right, you have a bit. That's the fundamental piece of the computer, and it can either be 0 or 1. And all things are binary choices in computers, right? And you basically build up your whole instruction set from binary numbers. But in a quantum computer, you can build what's called qubits, the quantum bit, out of superpositions of these things. So your memory or the thing you're working on can be in a superposition of many different choices all at once. And so we can use this to basically speed up calculations, and we can use this to allow us to simulate far more complicated systems. Here at Fermilab, we're using quantum systems as a tool to try to measure other things about nature. So we know there's this weird stuff out there called dark matter, and it's been very, very hard to find. But we can use quantum systems as very, very precise probes that look for the very feeble interactions dark matter has. And because we can manipulate these quantum systems so well now, we can put them into clever states that are useful for looking for dark matter and not for other things. So we can develop all these technologies to look for dark matter. We've got an ongoing, I think you'll probably hear about it on the tour. We've got ongoing work here to try to improve make better qubits, essentially, to make faster computers. Quantum mechanics is the reason we're able to build such cool things as lasers, MRI machines, iPhones, all these things. We don't understand how they work if we don't understand quantum mechanics. So all that technological revolution came out of these profound changes to our understanding of microscopic physics. But as I alluded to earlier, quantum mechanics isn't the end, right? Quantum mechanics is really the beginning of the quantum revolution. So if you take, was it last week that you did special relativity? You take E equals mc squared, all that special relativity stuff, and then you marry it up to quantum mechanics, you get something even weirder called quantum field theory. And when you have quantum field theory, you discover the idea of the vacuum of empty space is nonsense. There's no such thing as empty space. There's constantly electrons and positrons and other things popping in and out of the vacuum all the time. This chap, Dirac, helped combine quantum mechanics with special relativity and was led to the relativistic description of the electron and predicted the positron, which was then discovered. And if you go to pretty much any office in this building and look at the blackboard, you'll see crazy diagrams like this. So these are the ways working physicists talk about quantum field theory, and it allows us to describe how nature behaves, you know, at the LHC or the tevatron or things like that. And we don't even think quantum field theory is the final answer, but we don't know what the final answer is, and maybe somebody in this room will figure it out, and I'll stop there. Thank you. Sorry for almost running over.
No, I think we have time for a couple questions. I'll start with one. Well,
okay.
What do you do in your work?
What I do when I'm at work?
Or what do you work on?
I'm a field theorist, a theorist rather. I draw diagrams like this, and I look for ways theoretically to look for dark matter or to measure cool things at the LHC. So I use field theory every day. Yes.
So when two particles are entangled and then you separate them and then you mess with one and then you know how the other one's messed up. So how does this not violate the speed of light?
You're talking about the EPR,
yeah.
Einstein-Potansky-Rosen experiment. That's right. Because no information you can't use this to exchange information. So even though, you know, something you do here has changed something there, you can't do it in a controlled way. So there's no violation of causality. You can't use it to transmit information. Is basically the short answer. So EPR is another, I didn't get a chance to talk about it. EPR is another crazy side of quantum mechanics, but it doesn't violate causality. Thank goodness.
How does something like the particle trapped in a box experiment work in like a 3D environment? Because I know you showed like the atom.
Yeah, so the atom is the 3D version of it, and what happens is the math gets way more complicated, but it's essentially the same story. There are discrete energy levels, and you know the wave function has to fit inside the 3D box in just the right way. It's no longer a guitar string; it's
complicated things like Hermite polynomials, Laguerre polynomials, all sorts of, but it's essentially it's called.
So if math is built off of logic and set theory, which inherently have like a yes or no answer for things, how does that tie together with this, where the answer is
Maybe.
maybe?
Yeah, I don't know. I mean, quantum mechanics is still built on math. The description of quantum mechanics is mathematical. You just have to imagine that there are multiple answers to the yes/no question. And up until the moment you ask it, it can be yes or no at the same time.
How did Planck calculate like the Planck constant? Like, did he try to find it through like observation, or did he calculate
how do you measure? That's a great question. I think we got the first determination through the photoelectric effect. So where that threshold was, right? We can measure the electrons coming out of the metal, and we could work out what frequency of light gave us electrons coming out. And then there are other ways of measuring something called the work function of that metal, and you can relate the two and get Planck's constant that way. Yes, there's one here.
Okay, this is the last question.
Oh, better make it a good one, no pressure.
So in terms of qubits for quantum computing, how would you use the superposition to represent different like values to use the computers?
So I'm being kind of fast and loose, but what it allows you to do in some sense is to do multiple calculations at once, right? Whereas before, if this was one of your options and this was one of your options, you'd have to do one calculation then another calculation. In some sense, it's like I said, a bit of a hand-waving way of saying it. By putting it into a superposition, you can ask both questions at the same time. Now, you still have to collapse the wave function, so it's a little bit tricky because you still have to make a measurement. So, but the speed up is because of the superposition. It allows you to do many things at once. And I mean, we still have a long way to go. When I was a graduate student, people were talking about how awesome quantum computers were because they could, all of our internet traffic and internet purchases and credit card purchases, all those things are built on this famous algorithm called the RSA algorithm, which relies on, it's really hard to factorize numbers. But if I give you two 10-digit primes and multiply them together, but it don't tell you those primes, it's going to take you a long time to figure out what those two numbers are. And if you get this working, you'll be able to do that very, very quickly because you can try lots of primes at once, basically. But when I was a graduate student, they were very proud of the fact that they could factorize 15. So it's 15 is 3 times 5. Everybody knows that. But but we've come a long way since then, but we've still got a long way to go to actually get like a viable, the quantum version of my laptop has not yet been built, right? Something that you can carry around and do, but we're getting there. Okay.
So let's all thank the speaker one more time. Okay, so we're doing tours again. So if you were here last week, you would have done one tour, and we're going to rotate. Becky will help direct you. People on Zoom, Marcia, you can take it away. You'll have a virtual tour of the main injector, led by Maurice Ball, I believe.
Yeah, correct. It's about 20 to 25 minutes.
Awesome. So last week, who went to the SQMS tour? Okay, if you went to SQMS last week, you're going to stay here and tour Wilson Hall. Who went to the Wilson Hall tour last week? If you went to Wilson Hall, you're going to go to SciDet this week. So when you get out there, say that you're the SciDet tour. And who went to SciDet last week? You all are going to go to SQMS this week. Who went to no tours last week? 1, 2, 3, 4. Okay, what? Oh. So 3 of you, or 4 of you, so you're going to go with your dad. And I saw one hand over here. you're going to go to SQMS. I saw one hand over here. You're going to go to SciDet, one hand over another hand. You're going to stay here and do Wilson Hall, okay? Does everyone know where they're going? All right, everybody follow me out in the hall, and then we'll announce which tour guides you're going to be with.
All right, Marsha, you can take it away. I'll probably slowly shut down things here, but you're in charge.
Okay, thanks, Nate. Okay, everyone, in virtual land, I am going to share my screen now. And this is a video that is narrated by Maurice Ball. So I'm not going to talk this time other than to say goodbye, the tour is over. So I'm going to start sharing my screen now.
Hi, my name is Maurice Ball, and I'm a mechanical engineer in the Mechanical Support Department of the Accelerator Division. We provide mechanical engineering and technical support to the operations of the various particle accelerators at the laboratory. The main injector is one of those particle accelerators. This building that we're looking at here is one of the buildings that we use to enter and service the main injector enclosure. The main injector is considered the flagship particle accelerator enclosure at Fermilab. So let's take a quick look inside. Welcome to the main injector enclosure, where we are 40 feet underground in a 2-mile circumference ring where elementary particles are being accelerated up to 50,000 times per second around the ring. This enclosure is an interlock controlled area due to the hazards associated with particle acceleration. As a result, only qualified trained personnel are permitted to access this enclosure. However, today, using this virtual tour, I'm going to give you exclusive access to this truly amazing machine. But before I do that, let me tell you a little bit about myself and how I began my career at Fermilab. Here's a picture of me when I first started working at the lab. My first engineering project was right here in the main injector enclosure. Before working at Fermilab, I originally grew up in the South. A native of Texas, I received my bachelor's degree from Prairie View A&M University, just outside of Houston, Texas. After that, I completed my master's degree from the University of Wisconsin in Madison with a fellowship from the National Gym Consortium. This fellowship gave me the opportunity to intern at Fermilab. My first job was to design low conductivity water cooling systems for the main injector. These LCW systems keep the critical accelerator components at a precise temperature for prime operating conditions needed for accelerating the beam for the physics experiments. I used the knowledge that I acquired from my high school and college training. Classes such as geometry, algebra, trigonometry, chemistry in high school, and then in fluid mechanics and heat transfer in college, and of course, physics class. These were all used to help me design these systems. In fact, I still use these classes to this very day. One of my first big jobs was to design, specify, and install the secondary manifold piping in the main injector enclosure. So what exactly is the main injector? Well, the main injector is shown right here in this aerial view. It's actually the bottom oval ring in this photo. The particle beam of protons start their journey in the linear accelerator, followed by the booster accelerator beamline. The protons then enter the main injector enclosure, which actually houses 2 accelerator beamlines. From there, the protons are sent to various physics experiments throughout the lab, and even to experiments in other parts of the country. On-site experiments include the external beamlines, the muon campus, and the neutrino campus. All of these experiments are on-site here at Fermilab. However, there are off-site experiments also, as far as the state of Minnesota and soon South Dakota. By the way, I don't want to forget to mention here that Fermilab is known as the premier accelerator-based neutrino research capital of the world. So let's go back into the main injector enclosure for a closer look. Now, as I mentioned earlier, there are actually two particle accelerators in the main injector enclosure. One is called the main injector, and the other is called the recycler. These two particle accelerators work together to achieve two goals for physics experimenters. The first goal is to produce extremely intense particle beams, and the second goal is to accelerate those intense particle beams to extremely high energy levels. Now, here in this picture illustration are shown the two accelerator beam lines. The recycler ring is shown at the top of the image with the green magnets, and the main injector ring is shown at the bottom with the two red and blue magnets. After the particles enter the main injector enclosure from the booster accelerator, they are directed to the recycler ring. The recycler ring uses the permanent magnets, and that's the green boxes shown here at the top, to collect and store the particle beams arriving from the booster particle accelerator already. And when they enter the recycler, the protons are already at an energy level of 8 billion electron volts. The recycler ring arranges the protons into batches that follow each other around the ring. This batching allows the recycler to collect even more protons to create an even more intense beam. These intense proton beams then enter the main injector, shown in the lower section here, where they are accelerated up to extremely high energy levels, a staggering 120 billion electron volts. The red magnets shown here, also known as quadrupole magnets, have 4 magnetic poles. These poles focus and defocus the proton beam to keep the batch protons together and to keep them from repelling away from each other. The blue magnet shown here is called dipole magnets. They have 2 magnetic poles which steer the protons around the main injector ring, keeping them in the beam tube so that they can be brought back around and accelerated to the higher and higher energy levels with each trip around the ring. There's also other magnets including the octopole magnets, which is the orange tiny device shown here, the sextupole magnets, which is the yellow device, and then there's other magnets that's not shown here, like the trim magnets, the Lambertson magnets, kicker magnets, septum magnets, and permanent magnets. Now, one of the most amazing facts about these magnets is that they can weigh as little as 100 pounds or as much as 20 tons. Now, you can't go to a department store to buy a support stand to support such heavy devices. These support stands are one of the many engineering tasks that has to be on site by our resident engineers. Now, as a mechanical engineer, my task is to design fluid systems. As I mentioned earlier, I design low conductivity water cooling systems for the main injector. Now, in this picture here, you can actually see the piping and the tubing and the hose of various sizes and material makeup. And I use these to deliver and distribute the special water to cool these magnets. Now, if these magnets are not kept cool and at the right precise temperature, they will overheat, resulting in permanent damage to these magnets and quite possibly to the operation of the entire main injector accelerator machine. Now, in addition to the mechanical engineering of the magnets and the cooling water, there's also mechanical engineering of the vacuum systems for the beam tubes and electrical engineering for sending electrical power, controls, and instrumentation to the accelerator equipment. There's even civil and structural engineering for building the 2-mile circumference underground tunnel, which we're currently standing in via this virtual tour. Now, in addition to everything that I've mentioned here, and I've talked about so far, I would be completely remiss if I didn't mention one of the most important components of the main injector accelerator, radio frequency cavities, also known as RF cavities. These cavities are critical in that they accelerate or kick the proton particles to higher and higher energy with every trip around the ring. Now, all of the equipment that I've mentioned here, they all work together to manipulate and accelerate the proton beam in a specific manner as the beam propagates around the ring, with some of the particle batches spending an astounding 1.3 seconds duration circling the 2-mile ring before being extracted and sent off to the various physics experiments that I mentioned earlier. In fact, shown here in this next part of the tour is the main injector extraction region. Here, you can see the main injector and recycler beam lines on the left and extraction beam line on the right-hand side. This particular extraction beam line receives the extracted beam and then sends it to the neutrino experiments that I mentioned earlier. Now, I've been at the lab for many years, over 25 years, in fact. And even today, I still enjoy designing fluid systems for particle accelerators. However, because of my years of experience in fluid systems, instead of just being just a design engineer, I also now manage projects and the people who design and operate these systems. So as you can see, main injector is truly a flagship of science here at Fermilab, and engineers play a critical role in its design and operations. So thank you for touring the main injector with me.
Well, everyone, I thought the tour was a little longer. The tour is over for today. And I see that someone had a question about the name of the machine and why are these magnets used. And, you know, I can give you some idea based on the tours that were conducted last week. But quite honestly, I am not a physicist. So I would really prefer that you ask the question again next week when the physicists can give you a much better explanation than I can. So I apologize, but I would not be the one to give you the best answer to the questions. So that's it for class today. And so your attendance has been taken by Zoom, and remote people, enjoy the rest of your weekend, and please bring your questions next week about the magnets, and we'll see you next week then. Have a great weekend, and thank you again for being part of the program. Okay, take care, everyone. Bye.